Hi guys, welcome to the first podcast of cardiology, and today we are going to talk about physiology and all the basic things that we have learned in the first year. So we'll talk about cardiac cycle, then we'll talk about action potentials of SA node, AV node, like the pacemaker cells, and then we'll talk about action potentials of ventricles, and finally we'll talk something about cardiac output. Okay, so let's start with cardiac cycle. In layman's language or in very basic terms, cardiac cycle is the event happening between two heartbeats. Okay, whatever happens in the heart between the two heartbeats is cardiac cycle. Okay, so atrium and ventricle. So there is systole and diastole. And if we consider the heart rate as 72, then we get the duration of each cycle as 0.8 seconds. So this 0.8 seconds we have systole and diastole. So now whenever we talk about systole or diastole, we mostly refer to ventricles. So when the timing of systole is 0.3 seconds for the ventricles and diastole is 0.4 seconds for the ventricles. Okay, if we specifically talk about atria, then systole is 0.1 second and diastole is 0.7 seconds. Okay, now let's divide this 0.8 second in 8 parts. Okay, and now let's just talk about ventricles. So the systole is 0.3 seconds. Okay, and systole is what? It is contraction. It is the contraction of the ventricles. And if we draw a cardiac cycle, then the systole lies between S1 and S2. S1 is due to closure of mitral valve or both AV valves when the ventricles start contracting, and S2 is closure of aortic valve or pulmonary valve when the ventricles start relaxing, start diastole. So between S1 and S2, whatever is there, it's systole, and from S2 to the next S1 is diastole. Okay, now let's start from S1. So now ventricles have started contracting. The pressure in the ventricle is more than atrium. The mitral valve closes. There is S1 sound. Okay, now the pressure in the ventricle is more than that of the atrium, the left atrium, which is around 5 or to 8 mmHg, and it is less than that in aorta, which is 80 mmHg. So between 5 to 80, the ventricle is contracting, but the blood isn't going anywhere. It's just there in the ventricles. So this is called isovolumetric contraction. Okay, the volume remains same, just the ventricle is contracting and pressure is increasing. So this is isovolumetric contraction. Now, when the pressure in the ventricles rises above that of the aorta, then the aortic valve opens. Okay, and the blood starts to gush out in the aorta. This phase is known as rapid ejection phase. So the blood rapidly goes in the aorta. Okay, and the pressure goes on increasing till 120 mmHg. Okay, after that the pressure starts decreasing, but the aortic valves don't close, because when the pressure in the ventricle decreases, the pressure in the aorta also decreases. So even at this time, when the pressure in ventricle is decreasing from 120 to 80, the blood is still going into the aorta, but the rate at which it is going is slower. So the second phase was rapid filling, and now this phase is phase of slow filling or slow ejection. Sorry, not filling, ejection. So the second phase was rapid ejection, and this phase is slow ejection. After that, when the pressure in the ventricle drops below 80, the aortic valve closes. Why? Because the pressure in the aorta is 80 mm. Because there is blood in the aorta, the pressure is there. The pressure in the aorta is 80 mmHg. But the ventricle is relaxing, so the pressure in the ventricle falls below 80 and aortic valve closes, and there is S2 sound. Now diastole starts. So first phase is protodiastole. It's just the phase after which S2 closes. Then there is isovolumetric relaxation. Similar to what we saw in isovolumetric contraction, here both the valves are closed, aortic and mitral valve, both are closed, but the ventricle is relaxing. So that is isovolumetric relaxation. Now when everything was relaxing, the atria was getting filled with the blood because of venous return. Okay, and the moment the pressure in the ventricle is lower than that of the atrium, the blood which is in the atrium goes into the ventricles. So this is the phase of rapid filling. Okay, immediately most of the blood in the atrium rapidly fills the ventricles. Okay, so there is phase of rapid filling, and then there is a phase of slow filling. Okay, so 70 to 80% of the blood enters into the ventricles in this phase, the phase of rapid filling and phase of slow filling. After this, the atria contracts, and whatever the remaining 20%, 30% blood is there, it goes into the ventricles. So this is the phase of active filling. And then once the ventricle is filled, when it starts contracting, again there is closure of mitral valve and there is S1 sound. So again we come back to the cycle. So this is the entire cycle, and we talked about the 8 phases in the cycle. Now let's see some values, some pressures in the various chambers. So right atrium, the maximum pressure is around 5 mmHg. In left atrium it is around 8 mmHg. In right ventricle it is 25, and in left ventricle it is around 120 mmHg. Okay, so these are the maximum pressures in each chambers. Okay, now let's talk about action potential. Before talking about action potential, I would like to tell you 4 terms which you must have heard of: chronotropism, inotropism, dromotropism and bathmotropism. Okay, so chronology. What is chronology? One after the other. So chronotropic is heart rate. So it's the rate at which the next heartbeat is coming. Chronology. Okay. The next term is inotropy. So when we hear of ions, we think of contractility. Okay. So inotropy means myocardial contractility. Next is bathmotropy. So bathmotrophy is cardiac excitability. So how do you remember this? I searched for any specific meaning, but I remember this like when we take a bath in the morning, we are excited for the day. So bathmotropic is cardiac excitability, right? And last one, which is dromotropy, is cardiac conduction velocity. Okay, so dromotropism is conduction velocity, right? Now let's talk. Why do we need to know about these terms? Because chronotropism is associated with heart rate or SA node, and inotropism is associated with muscle contractility. Okay, so now why is the SA node the pacemaker? All the muscles of the heart have the ability to generate their own potential. Okay, every part of the heart can generate their own action potential. But why is SA node the pacemaker? Because the rate at which SA node can generate action potential is the highest. Okay, no other structure, other AV node, Purkinje fibers or ventricular muscles, none of them can generate the impulses as fast as SA node. That's why SA node predominates. Okay, and whatever firing is there, whatever the initiation is there, that's from the SA node. So in the action potential of SA node, we have 3 phases: prepotential, depolarization and repolarization. Okay, so there is something which makes this SA node or the other structures in the heart automatic. They have the automaticity. What is automaticity? It is the ability of generation of their own impulse without external stimuli, right? Like we have mechanoreceptors in our skin. So when someone touches it, there is some impulse or there is some stimuli because of which the impulse is generated. But so that's not automatic. But in the heart there is automaticity, which means even if there is no external stimuli, the heart can still generate its own potential, own impulse. Okay, so that is because of pacemaker potential. So there are three channels. Out of them, two are important. So one is funny sodium channel and the other one is inward rectifying potassium channel. So these are continuously open. Okay, so because of this, there is continuous, when the sodium channels are open, there is continuous influx of sodium and the potential keeps on rising. Okay, so as opposed to other structures in our body where we have a definite baseline potential or resting membrane potential, here in the pacemaker it's not like that. There is nothing called baseline or resting membrane potential. it is pre-potential or pacemaker potential. So funny sodium channels and inward rectifying potassium channels are there, due to which there is continuous increase of potential. So least potential is minus 60. Okay, from minus 60, when the funny sodium channels and inward rectifying potassium channels are open, this goes from minus 60 to goes on increasing to minus 40. And as soon as it reaches minus 40, there is the slope becomes steep and there is depolarization. Right? So this inward rectifying potassium channel is a special type where there is influx of potassium. Normally when we talk of potassium channel, we think of efflux because it's more in the intracellular compartment. But this is a special type which is inward rectifying, which brings potassium in. Okay. So these are, and one more channel is there, calcium channel, T-type calcium channel. So these three channels are responsible for pre-potential or pacemaker potential. Okay. This pacemaker potential is also known as restless potential because it's not stable. It's continuously increasing from minus 60 to minus 40. Okay. As it reaches minus 40, there is opening of L-type calcium channel and there is depolarization. Okay. The slope of pacemaker potential is less, but as soon as it reaches minus 40, the slope becomes steep and there is depolarization. Right? And then there is opening of potassium channels, there is potassium efflux, and then there is repolarization. So three things: pacemaker potential, depolarization and repolarization. There is nothing called resting membrane potential, but if we want to say the minimum potential for cardiac for the pacemaker cells, then that is minus 60 millivolts, and it fires at minus 40 millivolts. Now who controls this? So basically it's on its own. No one can start it or stop it, but obviously autonomic nervous system controls the rate. So intrinsic rate of SA node is around 100, but actually our heart rate is around 70 to 80, 72. Right? Why is it so? Why is it less? Because there is parasympathetic dominance. So parasympathetic nerve or parasympathetic nervous system decreases the slope of this pre-potential or pacemaker potential. Okay, and sympathetic system increases the slope. So depending on which system is predominating or which system is more active, the heart rate will be determined mainly by the slope of the pacemaker potential. Okay, right. Now this is about pacemaker potential. Now let's talk about ventricular action potential. So now ventricular action potential is something different. This has a resting membrane potential, and when the impulse from the SA node arrives, it depolarizes. So here we have 5 phases: phase 0, 1, 2, 3 and 4. Right? So phase 0 is depolarization. Here depolarization is due to sodium influx. In the pacemaker cells, it was due to calcium influx. So the potential rises from minus 90 millivolt. Here it's minus 90. Okay, the resting membrane potential for ventricular muscles or ventricular action potential is minus 90. In the pacemaker it was minus 60. Here it is minus 90. So as soon as the impulse arrives from the SA node, the potential from minus 90 goes up to plus 30 to plus 40. Okay, so this is phase 0, which is depolarization. Then there is phase 1, which is early repolarization. This is due to transient outward potassium channels. Okay, here the potassium channels open, which are transient, which move the potassium from inside the cell to the outside cell. So there is slight decrease in the potential from plus 20 to plus 30 to around plus 10. There is slight decrease, and then there is opening of, this is phase 1, and then there is opening of calcium channel. Okay, so because of this calcium channel, the calcium is coming into the cell, but the slow rectifier potassium channel are still open. So potassium is going outside the cell. There is a balance and the potential remains the same. This phase 2 is known as plateau potential. Okay, here also there is L type of calcium channel. We have seen T type, where T type in the pre-potential or pacemaker potential, L type calcium channel in depolarization phase of SA node, and in plateau potential of ventricular action potential. Okay, so in this in these three cases, in these three phases, there is a role of calcium channel. Okay, two types of calcium channel, L type and T type. Right, so now there is plateau potential. After this, the calcium channel close and slow and rapid rectifier potassium channels open. So this potassium channel take the potassium outside the cell, and then this is the phase 3, which is known as phase of repolarization. Right, and after the potential reaches minus 90, then there is resting membrane potential, which is due to sodium potassium ATPase channel pump. Okay, so 5 phases. Phase 0 is depolarization due to sodium channel. Phase 1 is early repolarization, which is due to opening of transient potassium channels. Then there is phase 2, which is plateau phase, which is mainly due to calcium channels. Phase 3, which is late repolarization, which is due to slow and rapid delayed rectifier potassium channels. And phase 4, which is resting membrane potential, which is due to sodium potassium ATPase pump. Okay. So that was about the ventricular action potential. Coming on to the last topic, which is cardiac output. So as you all know, cardiac output is stroke volume into heart rate. Stroke volume is determined by the contractility of the heart, preload and afterload, and the heart rate is determined by sympathetic or parasympathetic, which one is predominant, that will decide the heart rate. Right, we have seen that. Now what is preload? It is the venous return to the ventricles. So more the preload, more the dilatation of the ventricles, more the end diastolic volume, more will be the stretching, and by the Frank-Starling law, there will be increased contractility. Okay, obviously under the physiological limits, but that's all. So end diastolic volume determines the contractility of the heart. It is one of the factors which determine the contractility of the heart. Next is afterload. Afterload is the pressure against which the ventricles have to pump. Right? So if the afterload is higher, the cardiac output will be lower. So the afterload is inversely proportional to the cardiac output. Okay? The afterload is the resistance felt by the ventricles against which it has to pump. Right? So how is the preload determined? How do we estimate preload? It is estimated by end diastolic volume. Afterload is estimated by peripheral vascular resistance, and contractility is estimated by ejection fraction. Okay, what is ejection fraction? It is the amount of blood ejected into the aorta divided by amount of blood which was initially present, that is end diastolic volume. Okay, after the diastole, the amount of blood which was present is in the denominator, and out of that, the amount which was pumped out, which was ejected, is in the numerator, and we multiply this by 100. So normally ejection fraction is around 60-65%. Okay, so end diastolic volume is around 120 ml and ejected volume is 70-75 ml. So the ejection fractions comes out to be 65%. Okay, so that's it. I'll sum up the channel names and what's their role for the last time. So we have calcium channel, two types of calcium channel, L type and T type. Okay, T is transient, which is transiently open, and so this T type of calcium channel has a role in the pre-potential or pacemaker potential, which is one of the factors which helps the pacemaker potential to go from -60 to -40, and this -40 is known as threshold potential. This is T type calcium channel. L type calcium channel has two roles, one in the depolarization phase of pacemaker potential and in the plateau phase of ventricular potential. Okay, that is about L type calcium channel. Now coming on to potassium channel. So potassium channel, we saw inward rectifying potassium channel, which is responsible for pre-potential. Then transient potassium channel, which are responsible for early repolarization in the ventricular potential. And then there is slow and rapid potassium channels, which are for the late repolarization in the ventricles and repolarization in the pacemaker cells. Right, and sodium channel, as you all know, is for the depolarization of the ventricular action potential. Right, so that's all. See you in the next podcast. Next we'll talk about pulse, JVP, and also some pharmacology. Okay, so see you in the next podcast. Bye bye.